Lesson 6C, Projectile Motion, Object Thrown Upwards, Problem Solving. Example number 1. You fire a rocket straight up into the air with an initial velocity of plus 700 meters per second. Under ideal conditions, the initial velocity in the y-plane upwards would be plus 700 meters per second. The acceleration is equal to g, which is negative 9.8 meters per second squared. The rocket will rise but will begin slowing down, as denoted by the shortening displacements. When it arrives at the top, it will have a velocity final of 0 meters per second, denoted by the v subscript tf. Question number 1. What is the maximum height reached for the rocket? Well, again, the initial velocity is plus 700 meters per second. The acceleration due to gravity is negative 9.8 meters per second squared. The final velocity in the vertical will be 0 meters per second. Which kinematic equation do we choose? 1, 2, 3, or 4? We don't have time interval to use equation 1, 2, or 3, so we'll have to use equation 4 manipulating for d. Let's plug and chug. Vf squared equals vi squared plus 2ad. Plug in Vf, Vi, and A, manipulate the equation solving for d. We get negative 490,000 divided by negative 19.6. Displacement is 25,000 meters, or distance upwards is 25,000 meters. If this is true, the distance that the rocket needs to fall to arrive back at its origin is negative 25,000 meters. D down would be 25,000 meters. Question number 2. How long does this trip take? Here are the initial values given, Vi, g, and velocity to the top final. We now have calculated distance up and distance down. Which kinematic equation do we use? 1, 2, 3, or 4? We know initial velocity, final velocity, distance up, and gravity, which means 1, 2, and 3 may be used. 4 does not include time in this equation, so we can't use it to directly solve for t. Let's try equation number 1. D equals Vi plus Vf over 2 times delta t. Sub in d, Vi, and Vf. Isolate for t time up, which is 25,000 divided by 350. The time required to travel up to a distance of 25,000 meters with an initial velocity of 700 meters per second is 71.43 seconds. Question number 3. How long does it take to fall? Earlier we had stated that it would take an equal amount of time to rise to 0 meters per second as well as to fall from 0 meters per second, arriving at its origin. We will use this example to prove that this fact is true. Here are the values provided: Vi, g, vtf, d up, and d down, as well as time up, which we just calculated. Now as the object turns and starts to drop, it will displace greater and greater, meaning it's increasing its velocity at a rate of negative 9.8 meters per second squared. The velocity final at the top is 0 meters per second, meaning that the velocity at the top initially for the drop is also 0 meters per second. Which formula do we use? 1, 2, 3, or 4? Again, it looks like we should be able to use 1, 2, or 3 as they all include time interval in their formulas. 4 will not work as it does not. Equation 1 and 3 may be used if you assume the final velocity of the falling rocket will have the same magnitude as the initial velocity upwards of 700 meters per second. Since we are not 100% certain of this, formula 2 is our best bet. Let's use it and plug and chug. Substitute in d, vi, t, and a. Since initial velocity is 0, t squared equals negative 2,500 divided by half of negative 9.8. T squared equals negative 25,000 divided by negative 4.9. T squared equals 5,100.2. T equals 71.43 seconds. The time for the rocket to fall back down is 71.43 seconds, which is, coincidentally, the same amount of time for the rocket to reach its peak upwards. Question number 4. What is the rocket's velocity as it strikes the ground? Again, here are the values given or calculated earlier. Vi, g, vtf, d up, d down, t up, velocity, time initial, and just recently calculated time down, 71.43 seconds. Now which equation do we use? 1, 2, 3, or 4? With all the values to the left, it looks like we can use any of the 4. Let's choose formula number 3, which has yet to be used in the examples. D equals Vft minus 1/2 at squared. Sub in values for d, t, and a. Simplify the last term to 25,001. Manipulate to solve for Vf. Vf equals negative 700 meters per second, or 700 meters per second downwards. This is the same magnitude as the initial velocity upwards, but in the opposite direction, which is expected as the rocket is falling. For our rocket example, our initial velocity is plus 700 meters per second. Our final velocity was negative 700 meters per second. Velocity at the top was 0 meters per second. The displacement upwards was 25,000 meters. The displacement downwards was negative 25,000 meters. Time up and time down were both 71.43 seconds, and gravity was constant at negative 9.8 meters per second squared. To summarize, for vertical projectiles, initial speed equals final speed. The time up equals the time down. The distance up equals the distance down. The velocity at the top is 0 meters per second. Gravity is a constant at negative 9.8 meters per second squared.